Okay, let's do page 7 of chi-squared, and specifically goodness of fit, GOF. Okay, so number 1, Percy sows 3 seeds in each of 50 different pots. The probability that a seed will germinate is 0.75. The number of seeds that will germinate in each pot is shown below. So this is not normal distribution. Now it's binomial distribution. And the difference you'll see between normal distribution and binomial distribution is that usually binomial distribution, what you're going to have is you're going to have individual numbers here instead of intervals. You remember in the last couple pages we were using intervals, and binomial distribution you just have like the number of occurrences are just going to be integers here. Okay. So we only have 4 categories here, 0, 1, 2, 3. And they just like before, where half the problem was a normal distribution problem, the other half was a chi-squared GOF problem. Now the first half is going to be a binomial distribution problem. So instead of, remember we always used normal CDF before? Now we're always going to be using binomial PDF, probably. Okay? All right. So it says that the probability of seed germinating is 0.75, and the number of seeds that will germinate in each pot is going to be 0, 1, 2, or 3. So right here, using the capital B notation, they tell us that the number of trials, or the maximum number of seeds that is going to be attempted, is 3, and the p-value is 0.75. So 3 is trials, and 0.75 is the p-value, and we're going to put that into binomial PDF. We just need to figure out what the x value is in each case. So we're going to put 3 for trials, and we're going to put 0.75 for p. And then what we're going to do is we're just going to plug in 0, 1, 2, 3, and each one is going to give us one of the expected probability. First do 0. And okay, I'm just going to make a little table, and it's also going to have 0, 1, 2, 3, and these are going to be the expected probabilities. So it's going to be 0.0156 for 0. And then I'm going to do the same thing for 1, 2, and 3. So what I can do is I can just put this here, copy paste it, and then I'll just put 1 here instead of 0. It'll give me the next value, which is going to be 0.1406. And then the 2, I'll do the same thing. I'll just go up here, grab it, copy paste, and then I'll put 2 instead of 1. 0.4219. And then I'll go up here, copy paste, and then I'll change the 2 to a 3. The last one is also 0.4219. Okay, and so these are my probabilities, and let's see what we're going to do with those eventually. Write down the table of expected frequencies. So what's the difference between what we just did here and what we want to do in part B? So we just did part A, actually. These are the probabilities, expected probabilities. What we want is the expected frequencies. So expected frequencies can be calculated from the expected probabilities by multiplying times the total number of, so it's like 50 pots, okay? So all we need to do is multiply each one of these numbers times 50, and that will give us the expected frequency. So instead of 0.0156, I'm going to multiply this times 50 pots, and that'll tell me how many pots there are in this column. It would be 0.781. And then I'm going to do the same thing with 0.1406. times 50 7.03, and then finally I do that with 0.4219. You can see I'm trying to avoid rounding, which is the best way to get the answer they get. So 21.1, and that's the same for both because the last two probabilities are both 0.4219. So I've just written down the expected frequencies for getting 0 seeds to germinate, 1 seed to germinate, 2 and 3 seeds to germinate. Okay, so that was part B. Part C, state whether or not there are any expected values less than 5 and combined results if required. Okay, so remember, if you have an expected frequency that's less than 5, then you need to maybe combine it with its neighbor. So let's make a new table, and the new table is going to combine categories 1 and 2, or the two first categories. So I'm going to have a category that's 0 and 1, then I'm going to have a category that's 2, and then I'm going to have a category that's 3. And so my expected frequencies are going to be 7.03 plus 0.781. So that's going to be this plus 0.781, right? So the expected frequency will be 7.82. And then the next two are just going to be 21.1. Those are fine. They're above 5, so we don't need to combine them. And then the next row is going to be the frequencies in the original table, the observed frequencies. So the first two I'm combining, so 5 plus 10 is 15. And then the next two are 15 and 20. Okay, so just the fact that the expected frequency was less than 5 made us combine the frequencies, even though you can see that the observed frequency of 15 is fine. Or the observed frequency of 5 and 10, those are both 5 and above, so those are both fine. But since the expected frequency was not above 5, then we combine them. So now we have a table that is smaller. We only have 3 elements, right? Okay. So that was part C. Part D, write down the number of degrees of freedom. So the number of degrees of freedom now is 3 minus 1 equals 2. Write down, oh, well, that was D. So 3 minus 1 equals 2 for this one. And then the next part says, determine the results of a goodness fit test at 5% significance level to find out the data fits a binomial distribution. Remember to write down the null and alternative hypotheses. Okay, so the null hypothesis is that with seeds germinating is distributed binomially. And then the alternative hypothesis that seeds germinating is not distributed binomially. Okay, that was the null hypothesis. Now we're going to put our data into StatEdit, into L1 and L2. And remember, L1 is going to be the observed frequency, L2 is going to be the expected frequencies. I wrote that here in the reversed order, but you need to put the observed frequencies first. So I'm going to do that offline and come back. Okay, so I put 15, 15, 20 into L1. I put 7.82, 21.1, 21.1 into L2. And then I do stat test chi-squared GOF, which is on the second page. And I don't need to do anything to L1 and L2. Those are already in the right place because that's where I put them. The degrees of freedom now is only 2 because I did 3 minus 1 is 2. And then I go down to calculate. And my chi-squared value is 8.41. And the p-value is 0.0149. And my chi-squared value of 8.41, that is bigger than 5.991. So that means we reject the null hypothesis according to the chi-squared value. And then if we compare the p-value to the significance level is 5%, which means we're going to compare 0.0149 to 0.05. We can see that it's smaller, which means we reject the null hypothesis also. Okay, so the seeds grown are not binomial distributed because we're rejecting the null hypothesis. And that's it for that one. Let's go to the last problem, which is number 3. So Esmeralda tosses 2 unbiased dice 250 times. I can already tell this is going to be binomial distribution because dice is a thing for binomial distribution. She records the number of 6s that she tosses. So if she tosses 2 dice, obviously the most number of 6s she's going to have in one turn is 2. So that's why you end up with 0, 1, 2 here. And so she does it 250 times. You can see that the 250, that 135 plus 105 plus 10, those add up to 250. So that's the total frequency is 250. So we're going to use the binomial expansion of trials equals 2 and probability equals 1/6 to complete this table here. So let's do that. So I'm going to go to second distribution, binomial PDF. Oops, that didn't work. Second distribution. Sometimes I click too fast. Second page, binomial PDF, and the trials is 2. And the probability is 1/6. You can just write 1 divided by 6 here. And the x value is 0 first. And I want to multiply that times 250 to get the expected frequency. (173.6). 173.6. Okay, and then I'm going to do the same thing with x equals 1. So I just copy this here, and I'm going to change the 0 to a 1. And the answer is 0.2777, and I'm going to multiply that times 250 to get the expected frequency. And the answer is 69.4. Which mysteriously is 10 times that number. State whether there are any expected values less than 5. No, so we don't need to do combination of categories. Write down the degrees of freedom. Again, it's 3 elements minus 1 equals 2. Determine the goodness of fit test, blah, blah, blah. So now we're going to run the goodness. Well, first we need to put the data into stat edit, of course. I'm just going to do that offline. I'm going to put 135, 105, 10 in L1, and then I'm going to put these numbers in L2. Do that offline. I'll be right back. Okay, so I just did that, and now I'm going to do stat test chi-squared GOF, which is on the second page, so I get there quicker by going up, enter. L1 and L2, I put my data, my observed and my expected frequencies there, so I don't need to change those. The degrees of freedom is 2 like last time, so I don't need to change that. I just go down to calculate and press enter. And the chi-squared value is 28.2, and the p-value is 7.55 times 10 to the negative 7th. And I'm just going to compare that to our critical value of 5.99. It's greater than 5.99, which means we reject the null hypothesis. And then the p-value is very small, so it's smaller than 0.05. So we also reject the null hypothesis. And wait a second, we didn't write down the null and alternative hypothesis. It says to remember to write down, but we forgot. Let me write it down. The null hypothesis is that dice rolls with 2 unbiased dice rolling 6s is binomial distributed. That was very awkward the way I said that. Let me see if I can think of a better way to say that. The number of 6s when rolling 2 unbiased dice is not binomial distributed, not binomially distributed. Okay, so that's the null hypothesis and the alternative hypothesis, and we have rejected them, so that means that they are not binomially distributed in this particular observation. Okay, they're supposed to be, but in this particular observation, maybe we need to do more trials or something. So I think we're done now. We are. That was the end of page 7, so we're done with this packet.